Good afternoon, everyone. Welcome to Tank Technology, webinar presented by Protego USA. Thank you all for taking the time out of your day to join us. I'm hoping that you find the presentation informative, educational, really engaging. The team have worked quite hard on putting together some really good information. We're going to run a live Q&A session throughout the webinar, so please feel free to ask any questions that you have. We've got a team of a panel sat behind the presentation who are ready and going to answer your questions along the way. Any of those questions we can't get round to, the team will answer after the presentation, and we'll get answers out to you by email. Okay, thank you all for coming. So my name's Brad Luckman. I am the sales manager for Protego USA. Now I'm going to hand you over to the sales team at Protego USA to get things going. So I'm going to hand you over to our first speaker, which is Joseph Jones. Thank you very much.
Thank you, Brad, and good morning, everyone. Welcome to our Tank Technology seminar. First off, just to go over a couple rules and reiterate everything that Brad said. We got quite a few people in here this morning, so everybody will be muted just to avoid any extra noises. If you have any questions, we'll have people on standby for the live Q&A. There'll also be time after the presentation if you wanted to set up a meeting with our sales team. Presenters today include Brian Anderson, Brad Luckman, Lee Maxwell, David Persons, and myself, Joseph Jones. We'd like to kick things off. We'd like to kick things off this by telling you just a little bit about us as a company. Our headquarters is in Germany, and globally we are the largest manufacturer of tank vents and flame arresters. First and foremost, we are a technology company focused on evolving and adapting with the standards, and in some cases exceeding the requirements. We have research and testing facilities for both vents and flame arresters, and are constantly designing or improving upon current designs. With flame arresters, we have a long-standing history and expertise to help select an arrestor tailored to your application. We also have various tank equipment products such as thief hatches, in-tank valves, or floating suction units. And lastly, what we're here to talk about today, we have a product line of conservation vents, emergency vents, pilot operated vents, and several special application vents. A little bit about us at Protego USA. We're based out of Charleston, South Carolina. What we produce, we make flame arresters up to 16-inch flange size. We also make conservation vents up to 12 inches and have some larger emergency vents available. We also can have our production team evaluate and service your Protego device if maintenance is required to bring it back to as new condition if possible. Application engineers are also on staff and available to provide sizing, process support, or answer any technical questions. Also, with help from Germany, we can provide engineering calculations if needed. On-site technical maintenance training is also a service we provide. We can have our regional managers come out and provide a lunch and learn presentation, or have our production specialists come out and provide maintenance training or service the products on site if necessary. Also, if you're interested, we can provide on-site demonstrations using our portable vent test rig. So now on to today's agenda for the webinar. David's going to kick things off and go over applicable venting standards and some limitations. Brian will be covering the different types of vents and some industry venting technology. And Lee will be going over leakage rate and some emission reduction strategies. And to wrap things up, I'll be going over selecting vents and sizing.
Hello, my name is David Person. I'm a regional sales manager, and I'm going to talk about tank venting standards and pressure vacuum limitations they may have. We're going to talk about the most common tank standards out there that we see, a difference between them, And also we're going to talk about the overpressure and vacuum protection, venting requirements, and the consequences if you have failing venting systems. The American Petroleum Industry, API, has established standards for design, fabrication, and construction of welded steel storage tanks, mainly for storing oil. The most popular tank standards are API 620, 650, and 12D and F. Another standard we often use is the venting standard, API 2000. And even though they're not related, but they are combined in the fact that we look at them to make sure that we size and select correctly. Storage tanks come in many shapes and designs. Some of the most common designs are fixed roof tanks, floating roof tanks, horizontal tanks, and vertical tanks. API 620 standard. API 620 governs the design and construction of very large and welded low pressure storage tanks. They're designed to operate at high temperature up to 250 F and all the way down to minus 350 degrees F. They also can be designed up to operating pressures to 15 PSI. Just want to make sure so everybody understands that this is just not the design pressure every tank will have. It's just the fact that this standard covers tanks that can be having operating pressures up to 15 PSI. These tanks are generally utilized for liquefied natural gas, LNG, or storage, as well as other chemicals which require higher internal design pressures. Tanks typically are very large, 300 feet in diameter or larger. Another very common, as I mentioned before, is API 650. API 650 is also known as the atmospheric tank standard. Again, it's for welded tanks for oil storage primarily. The design fabrication is also in this dictates how it's going to be inspected, how it's going to be erected, and so forth. The operating temperatures varies a little bit, and it go all the way up to 500 degrees Fahrenheit and down to minus 40 Fahrenheit. The internal design pressure is maxed to 2.5 PSI. And again, this is just to say that this standard covers tanks that can operate up to 2.5, and not necessarily meaning that a tank all tanks have this high of a design pressure. Like I said, this standard is utilized for atmospheric tanks, and products are typically crude oil, gasoline, chemicals, produced water, and ranging from very, very small tanks like 8 feet in diameter all the way up to 300 feet in diameters. You can find them very often in refineries, terminals, pipeline facilities, and other clients. API 12D and 12F are primarily, we find them in upstream oil field services. They are fabricated and erected either in field or manufactured in a shop and then shipped out to the site. This standard covers most of all the engineering that is required, and therefore it's a simpler design than the two that we looked at before. They have predetermined tank dimensions, and as well as design pressure and vacuum, and as well as the accessories and how these tanks needs to be tested. Not They are not designed for permanent use in critical facilities like in oil terminals. To compare them, and what is important for us here at Protego is to understand the limitations of these standards. In the table to the left here, you see the tank, what it's designed for. And in the 620, at 100%, that is what we call the maximum allowable working pressure. And it's the design pressure. This standard allows an overpressure of 10% for pump in and pump out and the influence of thermal effects. For fire case or emergency system malfunctions, it allows an overpressure of 20%. If you look on the right-hand side of the table, we look at what this affects the valve. We can see here that if you, for example, have an emergency event, you can set it at 100% of the design pressure and allow it to go all the way up to 20% over this pressure, 120. Or if you have a conservation vent only, you can set it at 100 and allow 10% if you have a vent that is designed with 10% overpressure. Contrary to 620, 650 is a little bit different. The internal pressure is at 100%, and that cannot be exceeded, nor in fire case or with conservation vent. And again, if you look to the right, what the valve is seeing, again, we have, for example, you can set the valve at 90% of the design pressure and having opening pressure or the max desired required flow at 100%. So there is a distinct difference between these two standards. 12F in this case, again, this is for smaller tanks, field erected or shop built, and then designed to be shipped out to sites. And here again, at 100%, there is the max internal pressure for relieving of pump in and thermal effects. But the maximum allowable allowance pressure in fire case is 50% over or 150%, which is a huge difference between 650 or the 620 standard. So again, if you have a conservation vent, you can set it at 90% of the design pressure and having it relieving at 100%. And then your emergency vent can now be set so it relieves fully at 150% of or 50% over the design pressure. So there are distinct differences which we take into account, and we look at any other standards that are out there. We will find out what the limitations are. So if there are questions regarding if you have a different a tank designed for different standard, we have that information and can help you to set it up correctly. I mentioned API 2000, which is a standard for calculating the required flow for pump in and pump out and atmospheric breathing and fire relief. The standard covers these tanks that we have talked about, but it also includes a couple of different other types of tanks, and The most important part is that this standard covers up to operating pressures to 15 psi, and that is important to keep in mind, because above 15 psi we are looking at high pressure, which is not covered under this standard. Later edition of this standard covers other products than oil, and which is made this standard very handy for other applications. And so we can now look at the required flows and sizing and selection for other types of chemicals and alcohol and so forth. In this standard, I also recommended practices for use of flame arresters, and this comes into play for if you're storing liquids that have flash points of less than 104 degrees Fahrenheit. Storage tanks must breathe. When being filled or emptied, when exposed to thermal influences like heating up due to sun radiation or cooling down due to heavy rain. This is what can happen if inbreeding is hampered or blocked. And here we have railroad cars being sucked in, and actually it doesn't take that much vacuum to ruin a tank. Likewise, if you have overpressure, overpressure is a little bit more difficult to achieve, but the damages can be very dire, and the results can be of very costly, and actually have in many cases where it have happened ended the company. And this is what can happen if emergency valve breathing vent is blocked or not sized correctly. And here in this case, we can just see how the connection between the wall and the roof is basically just burst open. And in this case here, everything inside the tank is pouring out. Conclusion: importance of following the standards. Low pressure doesn't mean low risk. Large volumes of material can be released out to the environment if integrity is compromised. Relief of hazardous material to atmosphere requires safer design with respect to pressure and vacuum equipment. And this is what my colleague is going to talk about. And therefore, there are very special details that we look at to making sure that we safeguard your investment in your tank, saving the environment, and making sure that we are in compliance with all regulations that are at hand. I'm now going to hand over to Brian, who will talk more about vents. Thank you.
Good morning. My name is Brian Anderson. I'm a regional sales manager. I cover Texas, Louisiana, Mississippi, Oklahoma, Kansas, and Arkansas. I'm part of Missouri. So what we're going to discuss now is the traditional conservation vent designs and technology. One thing that I want to point out is we're going to run through a majority of the devices we see out there. We're trying to capture the most popular because we can't run through every single design or deviation of that design. So we're really trying to capture 90% of the low pressure conservation tank vents, PVRVs, ERVs that we're focused on today. So that being said, we're going to look at a few things. First, we're going to look at the weight loaded design, the standard weight loaded conservation PVRV, a spring loaded PVRV, how they're different. We're also going to focus on the pilot operated valves, some of the technology that pilot operated valves use versus your conventional weight loaded or spring loaded devices. Then we'll focus on emergency vents. One thing that we really want to also focus on are the definitions. And the main reason we want to focus on the definitions is within this industry, there's a lot of different terms used. So we're just going to focus on using specific ones for the presentation so everyone is aware of the exact topic we're discussing at that point. In addition to that, we're going to go over some of the overpressure and the pallet designs. 100% overpressure, 10% overpressure, some of the advantages, and we will touch on a few special designs in the event that something falls outside the scope of a general PVRD. So what we're looking at right now is a conventional weight-loaded pallet valve. We consider this a direct acting valve. It's a rather simple design. The way it works is by using the dead weight to maintain pressure on the tank, or using dead weight to maintain vacuum as well. As I said, it's a fairly simple design. It's really considered a working vent. So its main purpose is to handle your pump in, pump out, thermal effects, things of that nature. So one of the advantages of this is it does tend to be a cost-effective unit. One of the limitations of these units is that they're normally only rated for about 1 PSI. If we do exceed beyond 1 PSI, then we transition to a spring-loaded design. So we like the spring-loaded design because if we're looking at a weight-loaded unit, even set at 1 PSI, with a 12-inch nozzle connection, the weight stack can weigh over 100 pounds. So if you can imagine trying to get 3 or 4 PSI, the amount of weight that would be required on that device would be rather high. And it also gives us a higher center of gravity. So we could result in unnecessary damage to the tank or personnel. So that's why we transition to that spring-loaded design after a 1 PSI setting. Helps make us a lot lighter. This one is also cost-effective, and its general design is rather simple, so it can be used in a variety of different applications and services. The other type of unit we look at is a pilot operated valve. So the advantage of the pilot operated valve is that it's got a tight operating range. The lift characteristic is very quick, within 10%, and the reseating characteristic is very low as well, within 7%. These units can be used as a main working vent, but one of the downsides is they can only be used in clean service. So the device itself uses this pilot line that you can see on both of these units to sense the internal pressure of the tank. The pressure is then routed to this individual pilot valve, where it applies pressure on the pallet or on the seat, pallet and seat itself, allowing the seal to get tighter as the pressure inside the tank increases. Once it hits the set pressure of the pilot line, it relieves the gases in this upper chamber and allows the main valve down here to lift open. So this is a very nice design, but one thing that should be considered is it's not good for a dirty service if that line were to get clogged. If it's clogged, then you run the risk of having that valve not open. So the use of filters and the inlet pressure losses need to really be considered here to ensure that they're not hampering the effects. It can be used up to 15 PSI as well, but they do tend to be a more expensive unit, and they are sensitive to pressure changes. In addition to that, what we often see also is the emergency vent. So the emergency vent is another weight-loaded or spring-loaded vent. It's designed to only lift in the event of an emergency. An example of that may be a fire or a runaway reaction. So these units often have much larger connections. Normally they're 20 inches or larger. Though on smaller tanks, we do have some units that are down to 8 inches. So one consequence of an emergency vent, and what it's important to know the sizing, is that they do tend to have a larger allowable leakage rate. Lee will discuss that further, but it is something we want to touch on. So following that up, now we're going to go through some of the definitions to make sure that everyone's familiar. Set pressure, set vacuum. Essentially, that's when there's enough pressure, it causes the pallet to lift off the seat. Same thing applies for vacuum. Overpressure, or your percent overpressure, is the amount of pressure, the percentage of pressure over the set pressure, and that's used to determine the settings either for other valves or to determine where you're flowing. The design pressure, design vacuum. So we have two definitions for this one, and I bring that up in case any of y'all are to receive a quote and review it. So the design pressure of the tank, that's the maximum pressure a tank can withstand. But if you receive a quote, that pressure is where our valve capacity is measured. It's important to note that we're not measuring the capacity at the set pressure. It's actually measured at some percentage over that. Reseating pressure or blowdown, this is one that often gets overlooked for the low pressure world. It's a very important topic though we're going to discuss as well. This is the point when the pallet is able to seal back against the seat. It's also important to note that the reseating pressure or your blowdown is going to be below your initial set pressure. The last thing we want to note is flow capacity, and that's the flow rate of a device at a specific pressure. For those of you familiar with API 2000, this chart probably looks familiar, but for those of you not so familiar, I'm going to run through it really quick to make sure everyone has a clear understanding. What we have here is our percent overpressure and the percent capacity at full lift of the pallet. What it's essentially showing is two different units, a weight-loaded pallet valve and a pilot-operated valve. As the pressure, or as the overpressure increases, it's going to require anywhere between 80 to 100% overpressure for a traditional weight-loaded pallet device to achieve full lift. A pilot valve only requires 10% overpressure to achieve full lift. So there's a distinct advantage here when we're looking at a weight loaded versus a pilot, because the pilot's going to give us a much wider operating range. What we're going to show now is how that proportional, or the weight loaded proportional lift pallet works. In this particular instance, the design pressure is 5 inches water column. So we're going to have a set pressure of 2.5 inches water column. You'll notice that as soon as that pressure reached 2.5 inches, the pallet started to lift, but it's really not until it achieves 5 inches water column when it's at full flow. Now, one thing that we discussed was blowdown. Here you'll see that we mark the blowdown as 30%. I'll discuss that a little bit further, but what we really have found through our testing at our facility is that 30% seems to be a good rule of thumb. And I'll go into that 30% a little later. Now, what Protego has done differently, we do have our own proprietary 10% lift pallet. So what that allows us to operate is you're going to have a lift characteristic very similar to a pilot operated valve. The way it functions is that as the pressure increases, we're going to go all the way up to 4.5 inches water column. As soon as it hits 4.5, we're actually capturing some of the escaping vapors to help give us a quicker lifting action. Now, where this differentiates, or where this is different from a pilot operated valve, is that the blowdown is still going to be significantly higher. So we, again, factor in 30% for the blowdown, and that gives us a reseating pressure of 3.1. So it's still going to be much higher than if we were to use that 100% overpressure technology. Now, one thing we also want to address is there are other ways to achieve 10% technology, but the most outside of using Protego's technology, when doing so, what we often see is that a valve is either oversized or multiple units are required. As Joe discussed, Protego is a research company primarily, This was done at our test facility. I'm going to go ahead and start the video, but what you'll see is that as the pressure increases, the pallet will begin to get higher and higher until it relieves enough capacity. So that 100% overpressure pallet design has been around since the 60s. That's conventional technology. Protego still has that technology, and we use it from time to time in rare instances. But what we'll show you now is the 10% overpressure pallet. So you'll see here, we've actually incorporated a lifting aid, as we would call it. And what that will do is give us that quick opening characteristic. And Protego has had this technology since, I believe, early 2000s. So it's not new to us. However, it is a little bit new to some of the customers that we're dealing with. Now, when we talk about blowdown, it's important to realize that API 2000 5th edition used to state that conservation vents did not have blowdown. And simply by looking at the two diagrams here, the one on the left, when your valve is seated, it has a much lower surface area contact with that vapor space, but as soon as that pallet lifts, we can tell its effective diameter has increased considerably, which is going to require a much lower pressure in order for that pallet to reseat. So beyond that, blowdown has not been discussed in detail. So through our research and our findings, what we generally say is that 30% is a good catch-all for blowdown. That covers a multitude of sizes, a multitude of different designs, and it really helps us provide one stable number, even though it's not necessarily required to provide that. When we do a quick valve setting comparison, we're looking at an API 650 tank here, and we've got three different designs. We've got a 10% overpressure design, a 40% overpressure pallet, and then also a 100% overpressure pallet. So the procedure to determine the set pressure for the valves with different overpressure characteristics, we need to consider the design pressure. In this case, it's that 650. That's our MAWP. So we know that with that being said, 650 tanks, we can't exceed that 100% overpressure. And so it requires us to have a much lower set pressure, resulting in the opening pressure minus the overpressure of the valve, which is the characteristic specific to each valve. In short, what we're showing here is that by using 10% overpressure technology, you're able to increase your operating range versus that 40% overpressure or that 100%. If the tank is based on 100% overpressure technology, just by using your emergency vent, you're going to automatically cut the design pressure in half. So some of the advantages of 10% technology: you have an increased operating pressure. You can often use smaller devices, or because you're getting more pressure out of that tank, you may be able to use smaller equipment. It helps reduce emissions. You're obviously going to see higher set pressures, and this really is the best technology for tanks that don't have a lot of design pressure and a lot of equipment. If we're looking at that 100% overpressure technology, one of the benefits, we know it has a lower blowdown. It can be cost effective, and in some specific inline applications, it will be more useful. For those not familiar with API 2000, what we have on the right is the test setup. So you're going to have your blower or your fan with your measuring device, a tank, and then there's going to be a connection to that conservation vent. And then if it's a pipe away, we'll have that indicated there as well. What we're really trying to show here is that connection is no greater than 1.5 times the connection of the vent itself. That's how we measure for flow. Something that may not be considered in normal tank design are some of the inlet line losses if you're going beyond that 1.5 connecting pipe. If you're going above that, then we need to take that into account because the pallet on that vent will not lift at the same pressure within that tank. If it's closer, then that's okay, but if it's, say, 4 times the length of the nozzle size, then we really do need to take that into consideration. Another thing to consider, if there's other equipment, maybe a gate valve or a butterfly valve or a flame arrestor, all of these can affect the flow and the lift characteristic. Now, if we have a pipe away unit, another thing that we need to consider is not only the inlet line losses, but also if there's going to be any superimposed back pressure or built up back pressure, because that can affect the lift characteristic of the valve as well. So for this video, what we're going to show is the effects of an improperly sized flame arrestor underneath a conservation vent. So you can see here you have that arrestor and the pallet is sitting there chattering or simmering. So this is going to lead to premature wear. It's going to severely harm the seal of that device, and it's going to prevent other equipment from functioning properly. Now, we're going to look at that valve as it's intended to perform without the flame arrestor. What you can see here is that it's got a much more stabilized lift. The flow is consistent, and we don't have that chattering or that hammering effect because we've eliminated the device underneath it. This is some of the examples we like to use when we come up with our special designs. If you do have an intention of putting a flame arrestor with a conservation vent, we've come up with this unique device here. One of the benefits of it is that it has actually all the capacity provided has accounted for the pressure drop across the flame arrestor already for pressure and vacuum. So it has pressure relief, vacuum relief, and they still only require 10% overpressure to be fully open. Now, if you have a standard conservation vent that we discussed before and an arrestor underneath it, you're going to have to take into account that pressure loss across the arrestor before you can determine the correct capacities and settings. One of the other advantages for this unit that Lee will discuss is it has a metallic seal, but also my personal favorite is the easy maintenance design. So for this particular unit, you just have to take off one nut, take off this bolt, and then you can easily clean that arrestor in place if so desired, but it takes about 15 minutes. Another example of a special design that goes beyond the scope of API, this particular unit is good for polymerizing and freezing applications, polymerizing vapors and freezing applications. So its intention, it was designed for styrene or acrylates. It has the ability to work in high moisture applications such as digesters, and it can function all the way down to -40 Fahrenheit without the need for any sort of steam jacketing or heat tracing. One of the benefits of it as well, if we get to higher settings, is it can actually work as a dynamic deflagration flame arrestor, and it can also work against the endurance burn as well. In addition to that, just something else that may be of interest for those attending, this is a superheated vacuum breaker. This particular unit works great for asphalt storage or Storage tanks where you have to keep the process temperature very high so that you don't have sticking. So the way this particular unit works is it actually heats up the incoming air so that even if it's cold out, it's still heated to prevent buildup between the seat and the pallet, which could lead to sticking in the future. The steam jacket is also goes down to the flange, so it eliminates cold spots, and in some cases we have a PTFE cone that goes on top, and we do that in the event that there may be some product that sits on top of the cone. It'll allow it to slide off and prevent the vacuum setting from changing. So with that being said, I'm going to pass it over to Lee. Thank you for everyone's attention.
My name's Lee Maxwell, and I'm going to talk with you about leakage rates. Some of the topics we're going to go over: it's allowable leakage per API 2000, leakage measurement, the types of sealing technology that we use, how we perform our testing, and some of the advantages and disadvantages of the different types of seals. So allowable leakage per API 2000, you have it below. You can see it depends on the vent size. As you go up in size, you're allowed more leakage. And API, they recommend you measure at 75% of your set point. Some things to note about API: it's only a guideline. It's not a hard and fast standard like ASME where you have to meet this. And this is agreed upon by vent manufacturers as leak rates that they can all meet. And another big point of this is for new devices, something that's brand new out of the box. And we compare this with Protego's internal standard, where we measure at 90% of the set point. And if you compare some of these numbers with the API standard, we are significantly lower. Even on the large size vents, we still have very low leak rates in comparison to API. So we go beyond API, and what are the reasons for this? Well, we see a lot of advantages, a lot of things we can pass on to customers. One is increased confidence that your vent's going to function the way you want it to. A big one is product loss. You're going to have less with that lower leakage rate, and that really translates easily into savings. And you're going to have lower operational cost of this vent over the life of the vent. Another big one is increased safety. You're venting your product less, lowering exposure to whatever you have in your process. And the environmental impact, that's just keeping this stuff out of the environment. That's good for everybody. And when we combine this with our 10% lift technology, this gives us a lot more confidence with the higher set point, setting your valve closer to your blanketing pressure and being closer to your tank working pressure. Look at some of the different types of pallet designs, how we go beyond API. The types of pallet seals we have the metallic seals, such as 316 and titanium. And these are good for applications where you need that low leakage, and they do offer a low set point. These are good for nitrogen blanketing applications. We also offer the soft seal, such as FEP and PTFE. These are good for corrosive service or sticky service, something that might stick to that metal otherwise, or applications where you have chatter. These soft seals can provide a cushion if you have chatter due to irregular process conditions. And our valve seats, the standard is 316 stainless. We do have custom materials available. Brian showed some of the different types of custom devices. If you have something that's out of the ordinary, Protego certainly doesn't shy away from that. We ask you to bring that right to the table. So for our vent testing, we have a diagram on the right of our test rig. We test every vent that goes out of here, and we assemble them and test them as a whole unit. And what we're looking for on the pressure pallet, we test the set point and the leakage rate at 90%, and the same with the vacuum pallet. We test that set point and the leak rate. And what we're also looking for is the integrity of the housing to make sure you have no leaks in the housing itself or in any of the covers. So it's a pretty thorough test. And the way we test those leak rates, we increase the pressure inside the valve up to 90% of the set point, and we maintain whatever flow rate is required to keep that set point, to keep that pressure the same. So every valve that you buy from us, you'll have a test report that's available, and it does show the set point and the leak rate. These are serial number specific. They show you when it was tested, who tested it, and it's very transparent. And this is the type of thing you should be able to get regardless of the vent you buy, you know, from other manufacturers. So how do we maintain these low leak rates over time? As has been said before, we're an R&D company, and we do lots of testing. We do this in-house, and we test our vents that have been in use at customer sites. When we're building new vents in-house, we field simulate them, which is we let those pallets work a lot. We turn the flow rates up so that those pallets cycle to imitate what they would see in the field, and then we do our testing after we do that to make sure that they're going to seal even after they've been in use. In our manufacturing practices, we hand lap the seats on every valve. We have precision machine parts, and we use high quality materials. And these are all going to contribute to the low leak rates and the longevity of the device. We talk about some of the advantages and disadvantages, the different types of sealing. For the metal sealing, the advantage obviously is durability. We do have the low available set point even with that metal to metal seal, and these are low maintenance. And when we're looking at soft sealing, the advantages for these, they're good for sticky service. As I said before, they do provide a cushion if you have an application with chatter, and they have a very low set point. They can be set even lower than the metal. But some of the disadvantages with those soft sealing is wear. They do wear faster than the metal seal, and they're not really suitable for a higher set point. I'm going to turn it back over to Joe.
So now that you've heard about all the different standards, the types of vents, and some about the leakage rate, tying everything all together, here's a typical tank setup. Consists of a PVRV, an emergency vent, and a blanketing valve. Your PVRV can be thought of as the daily protection for the tank. It's typically sized to deal with your pump in and pump out rate, but also meant to deal with thermal expansion. Thermal expansion is as the tank heats up during the day, the vapor pressure increases, thus generating an outbreathing requirement. PVRV is also meant to deal with the sudden cooling of a tank, such as if there was a thunderstorm and it starts to rain, cool the vapor space and thus starting to condense, generating an in-breathing requirement. These vents are sized to have enough in and out breathing capacities for your daily plant operations. The emergency vent is, as the name states, for emergencies and should only operate in emergencies. Typically, these vents are sized based off several cases, such as runaway reactions, regulator failing, or fires, just to give a few examples. The worst case is typically used for the emergency vents capacity. These vents are sized so in your emergency case, the tank does not rupture. Your blanketing valve is typically used when volatile compounds are stored in the tank. Typically nitrogen is used as the media, and the valves are used so that during the tank outbreathing, nitrogen is vented instead of volatile compounds. So here you see two identical tanks. The one on the right is conventional 100% technology, and the one on the left is 10% technology. These are API 650 tanks, so if the MAWP of 8 inches is reached, the tank will rupture. And you'll see the pressure in the tank will start to rise. When the pressure reaches about 1.5 inches water column, the PVRV on 100% vent lifts, and when it reaches about 4 inches water column, the emergency vent lifts. At about 6 inches water column, the 10% vent lifts. Only on the 10% tank, only the PVRV lifts. So now that you've seen this scenario, how do we achieve this result? It's achieved through two things. One, the 10% technology, which results in a very quick acting and tight valve. That, coupled with our internal standards, we test our valves at 90% set point, exceeding API allowable leakage rates. Selecting set points for both the tanks from the previous scenario. First, we want to look at the ERV. We want it to be fully open at 8 inches, so we'll set at 7.3 inches to be fully open at the MAWP of the tank. For the PVRV, we want to make sure that there's no interference with the emergency valve, so we'll set that at 5.9 inches. You factor in the blowdown, and you can safely operate the tank between 0 and 4.5 inches water column. Now looking at the 100% technology, MAWP of the tank is 8 inches, so we have to set the emergency valve at 4 inches to be fully open at the MAWP. Using API's leakage rate at 75%, we need the PVRV to be fully open at 3 inches, so we'll set it at 1.5. Factor in the blowdown, and with the 100% technology, the tank can operate between 0 and 1.3 inches water column. If you wanted to use a blanketing valve on the 10%, you could operate at 1 inch, and on the 100%, you could operate all the way up to 3 inches water column. So now just a quick recap of that video as it went by pretty fast. We'll start with a red 10% technology. The emergency vent, we can set it using 10% technology, 10% below the MAWP of the tank, and using Protego's leakage rate at 90% of the ERV set. The PVRV, if it's fully open at 6.6 inches, there will be no interference between those two valves. And then taking the blowdown into consideration, that tank has an operating range between 0 and 4.5 inches water column. From this graphic, you can see the blowdown is greater on the 10% technology, but it still reseats sooner due to the higher set points. Now, recapping the 10% technology, the emergency vent needs to be set at half of the MAWP of the tank, so it will be fully open at the maximum pressure. Using API's leakage rate, the PVRV needs to be fully open at 3 inches. So then we'll set it at 1.5 inches, half of that. And taking that into consideration, the tank can be operated safely between 0 and 1.3 inches water column. So now, how does the 10% technology benefit you? Benefit minimum product loss resulting in cost savings. It gives you a wider range of operating pressure and minimized buildup of explosive atmospheres. All this is achieved due to the quick acting nature, tightness, and higher set points of the valve. Advantages of the 10% technology. One, cost savings. If we take the example of 2,800 cubic meters an hour, we can meet that flow with our 10% technology through one 6-inch vent, and with the conventional technology, it will take 2. This is because the higher set pressure results in more flow. If you look at the Protego tank, through one 6-inch vent, we're getting 2,900 cubic meters an hour. And through the 100% technology, only 1,900 cubic meters an hour through one vent. Downsizing is also an advantage. If you wanted to meet that flow using only one tank with the 100% technology, you would need one 8-inch vent to meet that flow. So now that we've covered set point selection and touched on some sizing, we'll move into sizing programs. All manufacturers have them, and for us at Protego, ours is Quest. It's an online-based sizing program, so you don't have to go through getting a program downloaded onto your desktop. You simply have to go to the website, click the link where you can log in or register. In Quest, there's a quick sizing option where you can select your vent model, size, and set points and get the capacities for that vent. The program also has capabilities of running full-on projects according to the latest edition of API 2000. For projects and quick sizing, it also has capabilities to give printouts as shown to the right in an easy to read PDF file. It also is capable of more challenging applications. If you're interested, please inquire with one of us and we can help. So that wraps up the presentation. Thank you for your attention and time taken out of your schedule. Feel free to contact or reach out to one of us at Protego if you have any upcoming projects or any other further questions or any other needs.
Okay, thank you, Joe, and thanks to all the other presenters today. I just wanted to just say again, thank you to all that have attended today's webinar. We hope you found it interesting. We've had some good questions along the way. If we haven't managed to answer any of those questions, we will answer the questions after the presentation and we'll get an answer to you as quickly as possible. We will make the information that you've seen today, we'll make that available via email after the presentation. Thank you for registering and giving us your details, so that will allow us to get the information to you pretty quickly. Okay, if there's any more questions, we'll stay online for another 15 minutes or so if you have any more questions to ask. Other than that, we'll hopefully speak to you soon. Thank you again. Bye for now.